Welcome to the Platform Engineering Playbook podcast, where everything you hear is built, reviewed, and improved by AI, by me, and by you, the listener. This show keeps me, and hopefully you, up to speed on the latest in platform engineering, SRE, DevOps, and production engineering. It's a living experiment in how AI can help us track, explain, and discuss the fast-moving world of infrastructure. Every episode is open source. If you've got something to add, correct, or challenge, head to platform-engineering-playbook.com. You'll find all the content and a link to the GitHub repo. Open a pull request, join the conversation, and make the playbook smarter. Let's get into it.
Today, we're diving into a fundamental shift in container security economics. Supply chain attacks are projected to cost businesses $60 billion globally in 2025. And the root cause of most container vulnerabilities? They're inherited from base images. Docker just made the solution free and open source.
But first, let's run through some major news that dropped this week. And we have to start with a historic first, Jordan. The Linux kernel Rust code has its first CVE.
CVE 2025-68260. This is a race condition in the Android binder Rust rewrite, affecting Linux 6.18 and newer. The vulnerability is in an unsafe code block, and it results in memory corruption that can cause a crash.
Let me break down what's actually happening here. The binder driver is Android's inter-process communication mechanism. The Rust rewrite was meant to be safer than the original C implementation. But here's where it gets interesting. The bug is in an unsafe block where the code manually manages memory lifetimes.
And unsafe blocks are essentially escape hatches from Rust's safety guarantees. You're telling the compiler, trust me, I know what I'm doing. In this case, there's a race condition where two threads can access the same memory region simultaneously, leading to corruption.
The key detail is that it's a denial of service issue, not remote code execution. The system crashes, but there's no ability for an attacker to take control or execute arbitrary code. Greg Kroah-Hartman, the Linux stable kernel maintainer, called this totally expected and normal.
What makes this significant is the framing. Rust doesn't eliminate all security issues. It eliminates certain classes of memory safety bugs in safe code. Unsafe blocks still need the same careful review that C code requires.
The Rust community will correctly point out this was in unsafe code. The skeptics will say Rust still has CVEs. Both miss the point. This is just normal software maintenance happening in a new language. The fact that we're at patch number 1 after years of Rust in the kernel actually validates the safety thesis for safe code.
Second story. GitHub Actions pricing changes are coming in January 2026, and the details are actually favorable for most teams.
GitHub is reducing hosted runner costs by up to 39%. The new larger runners, the 4, 8, 16, and 32 CPU variants, are seeing the biggest cuts. There's a new 0.2 cents per minute platform charge, but that's already baked into the reduced rates.
The self-hosted runner billing that had everyone worried postponed indefinitely. This is after significant community backlash when GitHub initially announced they'd start charging for self-hosted runner minutes.
The stat that matters, 96% of customers will see no change to their bill. Public repositories remain completely free. GitHub acknowledged they missed the mark on the self-hosted announcement and are going back to the community for feedback.
For that 4% affected, 85% are actually seeing decreases because of the hosted runner price cuts. The median increase for individual developers on private repos is under $2 per month. This is a case where community backlash actually worked.
The lesson for platform teams? Watch the pricing announcements, but don't panic. The economics of CI/CD infrastructure are still favorable, especially if you're using public repositories or have negotiated enterprise agreements.
All right, let's get into the main topic. Docker just made enterprise-grade container security free and open source. And Alex, this is a bigger deal than the headline suggests.
On December 17th, Docker announced they're releasing their entire catalog of over 1,000 hardened container images under the Apache 2.0 license. These were previously a commercial offering since May of this year. Now they're free.
Let's talk numbers first. These hardened images reduce vulnerabilities by up to 95% compared to standard community images. That's not marketing. That was independently validated by SRLabs, a well-known cybersecurity consultancy based in Berlin.
SRLabs ran penetration testing against these images and found no root escapes or high-severity container breakouts. The images are signed with cryptographic attestation, rootless by default, and shipped with complete software bill of materials plus vulnerability exploitability exchange data.
Let me explain the technical foundations here, because this is where it gets interesting. The core technology is what Docker calls Distroless Runtime. This isn't just stripping packages, it's a fundamentally different approach to building container images.
Traditional container images start with a full Linux distribution: Ubuntu, Debian, Alpine. They have shells, package managers, core utilities, all the tools you'd expect on a Linux system. A typical Python-based image might have 300 megabytes of stuff you never actually use at runtime.
With Distroless, you start from scratch and add only what's absolutely necessary to run your application. The language runtime, shared libraries, CA certificates for TLS, maybe time zone data. No shell, no apt-get, no wget, no curl. The attack surface reduction is dramatic.
If there's no shell, you can't drop to a shell. If there's no package manager, you can't install malicious packages. If there's no curl, you can't download payloads. The attacker's toolkit shrinks to whatever your application code can do.
But here's where Docker's approach differs from Google's Distroless project or Chainguard's Wolfie images. Docker is building on Debian and Alpine, the distributions teams already know. The file system layout is familiar, the debugging patterns are similar. It's distroless, but not alien.
Let's talk about the supply chain attestation, because this is what makes these images enterprise-ready. Every hardened image includes SLSA Level 3 provenance. SLSA, that's Supply Chain Levels for Software Artifacts, is a framework from Google originally that defines security guarantees for build systems.
Level 3 means the build process is hardened. There's non-falsifiable provenance, meaning you can cryptographically verify that a specific image came from a specific source at a specific time. The build environment is ephemeral and isolated. No human has direct access to the build infrastructure.
In practice, this means you can run cosign verify attestation against any Docker hardened image and get back a JSON document proving its origin. Your CI/CD pipeline can enforce that only images with valid SLSA Level 3 attestations get deployed. This isn't theoretical security, it's verifiable, auditable, automatable.
The software bill of materials, SBOM, is equally important. Every image ships with an SPDX format SBOM that lists every component, every library, every file in the image. When the next log4j happens, you can instantly query which images are affected.
Plus, there's VEX data, Vulnerability Exploitability Exchange. This is the context that vulnerability scanners lack. A CVE might exist in a library, but if the vulnerable code path is never executed in this image configuration, the VEX data tells you it's not exploitable. This dramatically reduces alert fatigue.
For platform engineers, that last part is critical. SBOM requirements are becoming standard. Executive Order 14028 in the U.S. mandated SBOM for government software. Similar regulations are coming in the EU with the Cyber Resilience Act. Having SBOM baked into your base images means you're not scrambling to generate it at build time.
Let's talk about the 7-day patch SLA. Docker commits to patching critical vulnerabilities within 7 days of disclosure. Compare that to community images where patches might take months or never arrive if the upstream maintainer is inactive.
The enterprise tier extends this to a 24-hour SLA roadmap, plus FIPS-enabled images for government and regulated industries, STIG-ready configurations, and extended lifecycle support. That's 5 years of patches beyond upstream end of life. If you're running Node.js 18 in 2028, you can still get security patches.
Now let's get practical. How do you actually migrate to hardened images? The key concept is multi-stage builds. Your Docker file has two stages. The first uses a full development image with all your build tools, compilers, test frameworks. The second copies just the built artifacts into the hardened runtime image.
Here's a concrete example. Say you have a Python Flask application. Stage 1 uses Python:3.12 to install dependencies and run tests. Stage 2 uses docker.io/library/Python:3.12/hardened, copies your wheels and application code, sets the entry point. Your final image has no pip, no setup tools, just the runtime.
The gotchas are in the details. Your application might assume /bin/sh exists for subprocess calls. It might expect /tmp to be writable. It might shell out to curl for health checks. These assumptions break in Distroless.
The debugging story also changes. You can't exec into a shell to poke around. Instead, you use ephemeral debug containers. Kubernetes supports this natively with kubectl debug. You attach a debug container with tools to the same pod, sharing the process namespace.
For local development, keep using full images. Multi-stage builds let you have both. Docker build target dev gives you the full environment. Docker build with no target gives you the hardened production image. Same Docker file, different outputs.
Let me explain why this matters so much for platform teams. If you're running 100 services in production and they all inherit from the same vulnerable base image, you have 100 services with the same vulnerability. The base image is the foundation of your entire container estate.
Traditional community images often have dozens or hundreds of CVEs in your vulnerability scanner. Most are unexploitable in your specific context, but your scanner doesn't know that. You spend engineering time triaging noise instead of fixing real issues. SRE teams get alert fatigue. Critical issues get missed.
With hardened images plus VEX data, the scanner knows what's actually exploitable. A CVE in libpng doesn't matter if your Python API server never processes images. The VEX document says, not exploitable, no affected code path. Your security dashboard goes from red to green.
There's also the compliance angle. FedRAMP, SOC 2, PCI DSS all have requirements around software composition and supply chain security. SLSA Level 3 provenance and SPDX SBOMs check multiple boxes. You're not just more secure, you're demonstrably more secure with audit-ready artifacts.
Let's address the elephant in the room. The developer community on sites like DevClass and Hacker News expressed wariness. Docker has a history of reducing free offerings and pushing subscriptions. Will this stay free?
Fair question. The Apache 2.0 license provides real protection here. If Docker changes course, you can fork the work. The SBOM and provenance data are portable. The image format is OCI standard. You're not locked into Docker Hub as a registry. These images work on any OCI-compliant registry.
The strategic calculus for Docker is probably about ecosystem adoption. If Docker hardened images become the default for production workloads, Docker Hub becomes more central to the container supply chain. That's valuable even without direct monetization of the base images.
There's also the enterprise upsell path. Free hardened images establish the value proposition. When you need guaranteed SLAs or FIPS compliance for that government contract or 5 years of support for your Java 17 monolith, the enterprise tier is waiting. Classic land and expand.
Let's compare the landscape. Chainguard has Wolfie, purpose-built from scratch for containers. Google has their Distroless images maintained by the open source community. Red Hat has UBI, Universal Base Image with REHL compatibility. Now, Docker enters with images built on familiar Debian and Alpine bases.
Each has trade-offs. Chainguard is arguably the most secure but requires learning a new ecosystem. Google Distroless is mature but community-maintained without commercial SLAs. Red Hat UBI is great if you're already in the REHL world. Docker offers the easiest migration path for teams already using Docker official images.
Let's talk practical steps for Monday morning. First, audit your current base images. Run a query against your container registry. How many unique base images are in use? How many CVEs are your vulnerability scanners reporting? Most organizations are surprised by both numbers.
Second, identify your top 5 most used base images. These are the ones inherited by the most services. If 80% of your containers use Python.3.11, that's where you start. The effort to impact ratio is highest for these common bases.
Third, check Docker Hub for hardened equivalents. The naming convention is straightforward. Look for the -hardened suffix in image tags. Python.3.12-hardened, Node.20-hardened, Nginx.1.25-hardened.
Fourth, create a test pipeline with hardened image variants. Don't do a big bang migration. Pick one service, swap the base image, run your test suite, verify functionality, compare vulnerability scanner output before and after.
Fifth, update your CI/CD to verify signatures. Use cosign or Docker Trust to verify image signatures before deployment. This closes the loop on supply chain security. You're not just using secure images, you're proving they haven't been tampered with.
The decision framework is simple. For production containers, where security matters, and it should always matter, use hardened images. For development environments where you need debugging tools and shells, community images are fine. Multi-stage builds give you both from the same Docker file.
The edge cases are niche applications without hardened variants, legacy systems that genuinely require shell access at runtime, or situations where the distro-less constraints break fundamental application assumptions. Those exist, but they're the minority.
And for those edge cases, at minimum, adopt the SBOM and signature verification practices. Even if you can't use hardened images everywhere, you can still dramatically improve your supply chain security posture.
The big picture takeaway here is that security has historically been expensive. Enterprise-grade container security was a line item, a procurement decision, something you had to budget for and justify to finance.
Docker just made it free and open source. For platform engineers building internal developer platforms, this is a quick win. Swap base images, get 95% fewer CVEs, check the SBOM compliance box, and close procurement tickets that have been open for months.
The supply chain security game changed on December 17, 2025. The question is how quickly your organization adapts. The images are available now under Apache 2.0 with no subscription required.
That's Docker hardened images, free security for every developer. And for platform teams, a rare opportunity where doing the right thing security-wise is also the easy thing.
That's it for this episode of the Platform Engineering Playbook podcast. Every topic, transcript, and summary you just heard lives out in the open at platform-engineering-playbook.com, where anyone can suggest updates or add insights through GitHub. If you've got thoughts, fixes, or new ideas, open a PR. And if you enjoyed the episode, rate us on your favorite podcast platform. We're always shooting for 5 stars. While you're there, give the project a star on GitHub. It helps others find and contribute to the Platform Engineering Playbook. This podcast is generated by AI, reviewed by AI, me and you, a community of engineers keeping our craft sharp. Thanks for listening, and see you next time inside the Platform Engineering Playbook.